Still under invariant structures, we are looking at conservative dynamics and Hamiltonian systems. In the other video, we had looked at manifolds and geometry and dynamical systems. So for conservative dynamics and Hamiltonian systems, we'll be looking at learning goals. By the end of this lesson, you will understand conservative dynamical systems, Hamiltonian formulation, phase space geometry, integrable systems, KAM theory, the conceptual theory. Then we'll look at chaos in Hamiltonian systems and some Python simulation methods. Of course, since we're looking at invariant structures, it gives an idea of things not changing, right? And that's why you can be talking about conservative dynamical systems. So let's go straight and talk about conservative dynamics. So a system is conservative if no energy is lost. That is, no energy. The conservation law of matter, right? Like I think is that in physics or chemistry that energy is never lost or never created nor destroyed, neither created nor destroyed, but it is changed from one form to another, or something like that. So that's the idea of conservation. So a system is conservative if no energy is lost. So we see that the total mechanical energy is always E equals T plus V. So that energy is constant. So T is kinetic energy and V is potential energy. So you can kinetic energy can convert to potential, some potential can become kinetic. But if you aggregate everything every time, you always get a fixed system. So in that case, we see that energy remains constant over time. And then we have a very good example of that in a simple pendulum where there's no friction, where we have energy to be E equals half ml squared theta dot squared plus mgl into 1 minus cos theta. So this is energy is conserved here because here you have the kinetic part and here you have the potential part of the energy. So why Hamiltonian mechanics? Why do we need to study Hamiltonian mechanics, for instance? So we have three formulations. We have the Newtonian formulation, which tells us that force is mass times acceleration, and we have the Lagrangian, which tells us that L is equal to T minus V. That's uh, kinetic energy minus potential energy is the Lagrangian. And the Hamiltonian tells us that I hope I'm getting this right. T is kinetic here. So Lagrangian formulation tells us that Lagrangian formulation is kinetic minus potential, while Hamiltonian tells us that H is equal to kinetic plus potential. So that's the idea of Hamiltonian mechanics. And the advantages is that this works in phase space, it reveals geometry and links to quantum mechanics, and it handles complex systems too. So for the Hamiltonian formulation, see how it goes. We have Q as position and P as momentum. So Hamiltonian then tells us that H of Q of PT. So if you express the Hamiltonian as a function of position and momentum, we have the kinetic as a function of momentum, and we have the potential as a function of position. Of course, kinetic talks about movement, while potential talks about energy. Kinetic energy is like energy at work, while potential energy is like energy waiting to work, right, in position. Okay. So, and then from that, we have potential Hamiltonian equations like for Q dot, we have H of P, partial H partial P, that's partial derivative of the Hamiltonian with respect to P. We have Q dot, then P dot is minus partial derivative of H with respect to Q. This replaces Newton's laws in this case now. We have an example here of the harmonic oscillator where h is p squared over 2m plus half kq squared, and you have the equations q dot is p over m, right? I mean, based on what we have there, q dot is partial h partial p. So differentiate this h with respect to p now. You have you have 2p over 2m. So 2 cancels out, you just have p over m. And there's no p here, so no worries. Then down here you have minus partial h partial q. So you have minus partial h partial q, that'll be half k times differentiate q squared, that's 2q. 2 cancels out, so you have p dot is minus q. So for the second order equation, then you get q dot dot. I mean, we can make this into second order equation. All you just need to do is try to, since we have p here, right? If you try to, if you make this p dot now, all right? Okay, this is what I'm trying to do. So we already see how we got all the q dot and p dot. Q dot is p over m, right? So q dot is p over m, and then p dot is minus KQ or something. Minus KQ, exactly. So it's minus KQ. But what are we doing? We want to make it into, just like we can make a second order equation into a set of a first order, two sets of first order equations. We can make two first order equations into a second order equation. What do we just do here? We know that if we do Q dot dot, that is equal to P dot, because P dot here now, Q dot dot means we have P dot all over M. And then we still have this one to be P dot equals minus KQ. Well, of course, we have married them together automatically. So this is now P dot, right? So we can have Q dot dot equals minus KQ over M because this is P dot up here. So we can then have MQ dot dot equals minus KQ. So I think that's how is formed right here. So that's why Q dot dot is K over MQ equals 0. Okay. So Q dot dot now. So we want to get Q dot dot together. So if you have MQ dot dot minus equals minus KQ, so that means we have MQ dot dot plus KQ equals 0. So if we divide through by M, so we have Q dot dot plus K over MQ equals 0. So we have converted that equation into a second order differential equation. Just like we can also split it up if we want. All we just need to do is to say P dot is Q dot is P over M, and then we split it up again. So here now we can assign values to those parameters and see what happens here. So for that, now we have harmonic oscillator simulation. So we assign value for M is 1, K is 1, the T, that's change in time is 0.001. T is 50, that's the kinetic. N is integer T over dt. Q is 1.0. And we do all of these things and just run the code and see what happens. So you want to study the code better in case you're interested in that. So this is one part of it. We see all these things, and then we see the second half of that too. So how everything plays out, and then we see the picture very soon. It's taking a bit of time. Um, okay, it's taking too much time. Still running. Okay, let's hope it finishes up pretty soon. Talking about the harmonic oscillator is it simulation or simulation? I think it's one of those. Let's say simulation. So waiting for that. Yeah, finally it's here. So we have time on the x-axis and we have Q on the y-axis. So that takes us to the idea of phase space geometry. So phase space consists of coordinates QP. Each point represents a complete system state. For 1D systems, we have 2D space, phase space. For n degrees, we have 2n dimensions like that, right? So, and then we have energy curve levels. So for energy conservation, we have the Hamiltonian of Q comma P is equal to energy. So motion lies on constant energy curves like that. And of course, we saw something close to this before, that harmonic oscillator phase curve can then be P squared over 2m plus half KQ squared equals Z. This represents an ellipse. And then we can do the phase space plot here. So PLT plot, we have the Q list, P list. So I'm sure it's still referring to the P list and Q list we got from here before. So if you did not run that, this is not going to work. So because this is just us plotting what we saw there. So look at what the phase space now looks like. So you have the Q list here, you have the P list. So, and all of this is giving us this, you have, it's more like uh the 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 line is building up, right? It's more like starting from inside and it's going out or coming from inside, anyhow you want to look at that. So we see that harmonic oscillator phase curve in that case. So we then have the symplectic structure. So Hamiltonian systems preserve area such that the Q intersection the P is constant. This implies no phase space contraction. This is Liouville's theorem. And that takes us to integrable systems. A system with n degrees of freedom is integrable if it has n independent conserved quantities, and these quantities commute under Poisson brackets. So for action angle variables now, imagine you have the coordinates QP corresponding to I theta. So you have the dynamic such that I dot is 0 and theta dot is omega of I now. Okay, so like a kind of coupled system. So if you solve this, you then have the solution to be theta of t equals omega t plus theta naught, like that. So as a result of that, you can then we can now go ahead and talk about invariant tori. That's it. Tori is plural for torus. So integrable motion lies on tori. So 1 degree of freedom talks about closed curves, 2 degree of freedom talks about two tori, and n degree of freedom talks about n tori. So motion in that case can be said to be quasi periodic. And I think I was in the last video, some videos before now, we had considered the idea of quasi periodicity. So, and this then takes us to the calm theory. So, talking about the calm theory from the conceptual side of things, so we have a perturbed Hamiltonian where H is equal to H naught plus epsilon plus epsilon H1, and H naught here can be said to be integrable from the definition of integrability we already saw up there. Now, the question is, what happens to the invariant Tori in this case? Okay, that's a question we ask ourselves in this situation. So, and then that takes us to so we're talking about CAM theory. So that takes us to the informal definition of the KAM theory. So, um, here now we have that most for small epsilon, most invariant Tori survive, right? Most invariant Tori survive, and some are destroyed, and chaos appears between them. Then we have phase space becoming a mixed bag, kind of. You have chaos appearing, most invariant Tori survive, and some are destroyed, and chaos appears in between, right? So you have phase space becoming mixed. So for the physical meaning of this is then that small perturbations do not destroy order completely. Then two, stability of the solar system. An example of that is the fact that the stability of the solar system, right? Small perturbations do not destroy order completely. And you have regular and chaotic motion coexist in this situation of a calm theorem. So you then have, okay, maybe I should go for calm theorem in layman language, right? Because this is sounding like a lot of jargon, right? Calm, calm theorem. Okay, calm theorem. That's Kolmogorov uh Arnold theorem. Uh in layman, as usual, let me do my layman thing. Layman terms, right? Okay, so here it says that the CAM theorem, named after Kolmogorov, Arnold, and Moser, is a fundamental concept in physics and mathematics that explains why many complex moving systems, like our solar system, remain stable and predictable rather than falling into chaos, even when small disruptions occur. Here is the CAM theory explained in layman's terms. The core idea is that order survives small changes. So if there's order, if it causes a bit of perturbation, maybe there's a light, just like in chemistry, when you talk about Le Chatelier's principle, if something goes wrong, the system balances out itself. So imagine a perfectly functioning, predictable system like a set of planets orbiting the sun without affecting each other. This is an integrable system. So it means they can work well together. We saw the idea of integrable system. It wasn't even this clear. So now introduce a small nudge or disruption, a perturbation, such as the planets slightly pulling on each other gravitationally. For a long time, scientists thought such disturbances would immediately make the system chaotic. But then the CAM theorem proves that this is false. So it stated that if this disruption is small enough, the majority of the original ordered motion survives, though it gets slightly deformed. That's all. So you can have the best you can have is like a share, but then it doesn't cause any significantly chaotic situation. So the shield of irrationality. Why don't all systems become chaotic? Then the theorem states that motions with sufficiently irrational frequencies survive. So, I mean, that's basically the idea. So, the summary is that, you know, complex systems like our solar system remain stable and predictable rather than falling into chaos, even when there is small disruption. So that's what we've been saying. So integrable system, if you look at it from the eye of what we've seen now, it tells you that everything can work together, though they have some impact on themselves once in a while. It doesn't actually cause any problem. Okay. So chaos in Hamiltonian systems. Hamiltonian systems can be chaotic even with energy conservation and volume preservation. They exhibit sensitive dependence. Of course, we've talked about the fact that chaotic systems are sensitive to initial conditions. So a little change in initial condition can lead to significant differences. So if you look at the Henon-Hell's Hamiltonian, so you have h is half into p sub x squared plus p sub y squared plus half into x squared plus y squared plus epsilon into x squared y minus 1 over 3y cubed. This system displays chaos, right? And we have the standard map. So you have Pn plus 1 equals P sub n plus 1 equals P sub n plus K sine Q sub n. And then you have Q sub n plus 1 equals Q sub n plus P sub n plus 1. This map shows transition to chaos. Okay. So, and with all of that in place, we have so we just want to represent all that. Now you have all the K equals 0 0.8, N is 20,000, you know, K now is, you can change this very 0 0.1, 0 0.5 and all this. And N is 2000, that's number of iterations you want. And number of orbits can be 6, that's number of initial conditions. So we can change all of this to see what the standard map looks like. So we run that and we have, I mean, you can keep, so see the kind of thing that happens there for K is 0 0.8. So it looks, as we keep running, it keeps changing in structure somehow. It just keeps changing. But of course, it's possible to be able to fix it. Like this is 0 0.8. Now, for apart from 0 0.8, now can let's change to 0 0.1 and see what happens. Okay, it's now 0 0.1. See what we get there. So let me run it once more. It might also change shape still. Yeah, we have this. Then I do 0 0.1 again. We have this. Okay, so you have the map changing like that. Then we can do 0 0.5. 0 0.8 was what we did before. So this is what 0 0.5 looks like that. Then we have, let's say 1.0 now, 1.0. So for 1.0, see what we have. Okay, I run it again with same 1.0. It's gonna change structure a little bit. Yeah. So we see all the issue happening there like that. So here we're doing modulo 2 pi torus geometry like that. So it's coming from all this P, K, sine Q, blah, 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 like this. So let me do 5.0. Let's go 5.0 and see what happens at that level. Okay, now see what's happening here. And I do it again. Okay, it's giving the same pattern more or less. So we can have all of this going. Let me do 2.0 and see if the structure is slightly different to, for the standard map. Okay, wow, see what this looks like. So it's like it keeps sh shifting like that. Okay. So let me just go on. Now we see that, of course, we saw Lyapunov exponent in the last video where we talked about quantifying chaos. So you have, for Lyapunov exponent, lambda is the limit as t tends to infinity of 1 over t ln delta of t over delta of 0. So if lambda is greater than 0, we have a chaotic system. If lambda is 0, we have a regular system. In summary, then, we say that conservative if we're talking about conservative, the key idea is that energy is conserved. For Hamiltonian, we have the total energy. For phase space, we have geometry of motion. For integrability, we have many constants. That is, like in the solar system, all the planets work together without falling into chaos. And we have the calm now. That's stability under perturbation. That you have a complex system working, even when there's a slight perturbation, it doesn't cause any issue. Then for chaos, we have sensitive dependence. We have a system that is sensitive to initial conditions. So a little bit of shift in initial condition can cause a large problem. So the big picture we see here then is that Hamiltonian systems describe planetary motion, molecular dynamics, plasma physics, quantum mechanics foundations, and they show how order evolves into chaos. So, and of course, as usual, we have our practice problems. Okay, let me take them in twos. Um, Energy conservation. Consider the harmonic oscillator. H is this. Derive the Hamiltonian equations. You follow the things we did before. Show that H is conserved. Verify conservation numerically. Then problem two, phase space geometry. For the Hamiltonian, H is this. Find the equations of motion. Sketch the phase space curves. Describe the qualitative motion. Want to check also the things I did previously. Three, pendulum. The pendulum Hamiltonian is this. Derive Hamiltonian equations. Linearize for small q. Compare with the harmonic oscillator. For numerical integration, I'll consider H is half into P squared plus Q squared. Simulate using Euler's method. Compute energy error. Repeat using a symplectic method and compare results. So for 5 and 6, we have phase, volume, and integrability. We have for 7 and 8, action variable and CAM perturbation. For 9 and 10, we have the standard map. I mean, just like all these ones I was showing before. And then we have Lyapunov exponents. Consider two nearby trajectories of a chaotic system. Well, if you try your hands on this and you're able to get it, you can let me know so I might be able to try solving it to see if I may make another video to solve this for you to see how that works. Okay, with this, I come to the end of this interesting video about conservative dynamics in Hamiltonian systems. And together with the previous video, on manifolds and geometry in dynamical systems, with we have treated the concept of invariant structures. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already to this channel, I thank you very much for doing that. And if you haven't subscribed, the question is why? Go ahead and subscribe right away. Hit the notification bell also so you can always get alerted each time a new video is released. Beyond that, you can become a member of this channel, and that comes with some special privileges like some videos made just for you as a member, or members get to see some videos before other people. We can hang out. I can consult for you on something that I do on this channel that is of interest to you and all that. So let's build this community together sweetly. And ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.